Okay, so we are in chapter 4 from Jonathan Wickett's book, which is Forces and Moments in the Structures and Machines, and we have talked about the concept of forces, we talked about the concept of moments, and we have said that, hey, the concept of force alone is not sufficient to make something rotate, right? Because you need that force applied at a certain distance away from the hinges to make something rotate. And that brought in the notion of the moment, where we had the concept of force, we had the concept of perpendicular distance from the hinge. Then we talked about Newton's 3 laws. Now, the last topic in this chapter is the topic of static equilibrium. Okay, so when you take 260, which is engineering statics class, this is what you'll be doing day in, day out in that class, right? So next 10-15 minutes are supposed to give you a flavor of what you would possibly learn in 260 class. And of course, you have a bunch of problems that you'll have to solve from your homework. And equilibrium analysis is something that you will also perform while doing some of your homework assignments on the homework board that we'll be giving to you very soon, perhaps in next 7 to 8 days' time, and also for the project, okay? So what is equilibrium? Well, equilibrium is defined by a very simple condition. The condition says that if you have a structure, if you have a machine, if you have a bunch of forces applied on it, then it is in equilibrium if sum of all the external forces acting on it is 0. Okay, so if somebody says that something is equilibrium, then you can simply apply this condition, sigma f equal to 0. All right? A second condition is that the net external moment about any point is 0. Remember, when you take the moment about a particular point, right? You've done some homework problems in your current homework due on Thursday where you had to compute the moment about certain points, right? Those were moments of maybe some forces only, and those moments may not be 0. But if something is in equilibrium, and if you take moment of all the external forces acting on that part about any point, the sum of that would be 0. That's the basic idea. So sigma f equal to 0 and sigma m equal to 0. That's it. Now you can use these two conditions to solve for some of the unknown quantities in the problem, right? So we'll look at an example pretty soon. So what is the process? What is the method for solving equilibrium problems? The method is very simple. First thing you will do is you'll draw the free body diagram of the isolated object. So you look at your object of interest. Now that object of interest may be just one single item or could be a collection of items, right? And you will draw the free body diagram of that. Now your free body diagram will show all the forces and the moments acting on it, right? That's the number one thing you'll do. Then you will apply the equilibrium condition, and the two equilibrium conditions are that you'll set net forces to 0. So you'll sum up all the forces acting on it and you equate it to 0. Now if you sum all the forces to be 0, and if you're writing the vector sum in a plane, let's say xy plane, then that would reduce to two scalar equations because you have components along I hat direction, you have components along j hat direction, and what you would essentially get is two scalar equations, right? Then you can also set the net moment about any point to 0. Now you can pick the point about which you want to compute the moment. There will be certain points that will be a better choice compared to others, right? And pretty soon you will see which points will be better in what situation. But you can pick any point, and about any point if you compute the net moment of all the external forces acting on it, then that would be equal to 0 as well. Now, the moment equation will give you only one scalar equation, right? Because the moment is either clockwise or counterclockwise. So either it is positive or negative. So there is no I hat or j hat. Essentially, that equation is along k hat direction, which is perpendicular to the xy plane. So if your forces and your position vectors are all in the xy plane, then the moments are always going to be in the z direction, right? So either it will be plus z or minus z, so you don't need to really say k hat. It's the sign that takes care of the direction. So essentially, you'll have no more than three scalar equations for each part which is in equilibrium, right? If you have three scalar equations, how many unknowns you can solve for at most? 3, that's it, right? So 3 equations, 3 unknowns. So that's what you would have to do. You have to count the unknowns and make sure that you have enough equations. If you find that your number of unknowns are 4 and you have only 3 equations, then chances are that maybe you have neglected something or you have accounted for something more than it needs to be. Or that maybe you need to actually do the analysis on 2 parts, not just 1 part, right? Because for each part you can get 3 equations. For 2 parts you can get up to 6 equations. And then finally you have to solve for the unknown quantities, right? And I say over here that it is sometimes simpler, more judicious to choose the pivot point about which you compute the moment to be the one where the forces are acting in such a way that you have least information about them. Okay? So for example, if let's say I draw a structure that looks like this. Okay, you have this structure, and you have a point over here. Maybe there's a hinge joint over here. Let's call this point A, and I have a force along x direction, force along y direction. Let me draw the coordinate system. Okay, a pin joint can support reactions along both x and y directions, so I have forces over there, and then somebody is pulling here with a force of F. All right, and problem tells you that this structure is in equilibrium. Okay, equilibrium is same as static equilibrium. The more precise thing to say is to say static equilibrium, but sometimes people just say equilibrium, and is the same as a static equilibrium. So if this structure is in equilibrium, then we know that some of the forces should be equal to 0 and some of the moment should be equal to 0. But if the question says that if this is an equilibrium, give me what this force F is. Okay, give me what this force F is. Let's say, just to make things a little bit more interesting, I have another force G over here. Okay, so two forces, F in this direction, G in this direction, and I want to know what F is. All right, and I already know what G is. Let's say this is given as 10 Newton. All right, so I can solve this problem by writing sigma F equal to 0, and I can write sigma M equal to 0, right? And I know that this is going to give me 2 equations, and this is going to give me 1 equation. So I'll have total 3 equations. From 3 equations, I can solve for 3 unknowns. Let's look at the problem. Just from the free body diagram, I can count the unknowns, right? I have F as 1 unknown, AX as 2nd unknown, and AY as 3rd unknown, right? G is already given to you. So you have 3 unknowns. You can solve for the 3 unknowns from this. So you can sum all the forces to be 0 along x direction, sum of the forces along y direction to be 0, and then you can take moment about some point. So now the question is, about which point should you compute the moment? I can take moment about, point A. I can take moment about, maybe let's say this point is C, and I can take moment about this point B, right? Or any other point. Doesn't even have to be a point of application of these 3 forces. I could pick, center of mass of this thing and say I will take moment about that point, right? But no matter which point I pick, sum of the moment about that point should be equal to 0. So in this question, if only F is being asked for, I am better off actually choosing point A as the point about which I will compute the moment. Why? Because if I take moment about point A, then what will be the moment of AX and AY? 0, because AX and AY are passing through point A, right? Pushing on the hinges. So there is no contribution in the moment quantity from AX and AY, because AX and AY are going through point A, right? Okay. What about moment due to force G? For that, I can try to find what the perpendicular is. So I have the line of action of G, I extend it, and then I drop a perpendicular from point A onto this. So using trigonometry and geometry, I could find that. Or if, let's say, I know the angle of G from horizontal, let's say this is theta, then I can resolve G along x direction and y direction and use the component method to solve for the moment of G. And I could do the same for the moment of F, right? I could either resolve it along component direction, or I could try to find the perpendicular to the line of action and multiply F with that, figure out what the sign would be, whether it will be positive or negative, and now I have only 1 equation where the only unknown is F. So just 1 moment equation, so sigma M about A equal to 0 gives me the answer. Because the question is not asking for AX and AY. So if the question is not asking for AX and AY, then you can choose that point as the point about which you compute the moment, so that you don't have to solve for AX and AY. And that's what I'm saying over here. It is simpler to choose the pivot point to be the one through which the forces are passing about which you have the least information. And AX and AY is something that the question is not asking for, so you can just choose that as the pivot point, right? Now, this is telling you that there is no one single way to solve the problem then, right? Because you could have just written sigma F equal to 0, and that would involve AX, AY, and components of G and F along x direction, as well as components of those in y direction, equated them to 0. And essentially, you would end up solving 3 linear equations in 3 unknowns, which will be simultaneous, and you would essentially get all the unknowns. You will know not only F, but also AX and AY. But if the question is not asking for AX and AY, then why necessarily waste your time doing this, right?